Okay. Thank you everyone for coming. It's my pleasure to introduce you to Professor Michele Bacciocchi here today. He's coming from San Marino, which is actually a small state, independent state within Italy. So he's not really Italian, even if he's coming from Italy. I have the pleasure of knowing Michele since many years. We did the bachelor and master together at the University of Bologna in Italy. And then I came to the US and he started his PhD in Bologna, actually. So he got a PhD in structural engineering from University of Bologna. And then he started doing some more computational work, I would say. So as you can see from the title of the presentation, it's pretty math-based. So I will let him show us this recent work that he completed in the recent years. And let's welcome him again.
Thank you very much. Thank you very much for being here. It's a pleasure to be invited here from Gloria. As she told, we met 15 years ago now. It's quite a long time, but it's my pleasure to be here in San Diego. And so for starting, as you can see, here's the title of the presentation. I will give you some details later, but before, I would like to spend some words about my country. As Gloria told you, I come from San Marino. We have a small university. There I will give you some details also about the university. But before, I will spend just a couple of minutes talking about San Marino. As you can read here in the slide, is a republic. Is an enclave in the central Italy, just in front of the Adriatic Sea. And the territory is really small, as you can see here. 23 square miles. I hope the conversion is okay.
That's smaller than the Vatican?
No, it should be bigger.
Okay.
Yeah. But what is interesting is the inhabitants. 34,000 inhabitants. And just for the sake of comparison, I put also the students enrolled here as SDSU in 2024 is really a lot more. It's interesting also for my side, for my point of view, to specify that San Marino is the oldest constitutional republic in the world, and it has been recognized by UNESCO as the testimony, as you can read here, of the institution of a representative democracy based upon civil autonomy and self-government. It's really old republic. And yeah.
Everybody with a collection of San Marino stamps here raise their hands.
Really?
I have a medal.
Really? Next time I have to bring something more, eh?
Yeah, you do? Okay.
I believe the secret is that because there are not that many people.
It's not my first time in
No, but I'm saying that the secret that it works and research harmony is because there are not that many people.
Yeah, that's correct. It's correct. But it's quite strange for me that people here know where is my country, and so I put also the map just to here specify that you can. It's just a dot in Italy. This is Europe, and if you, I don't even have the space to underline the territory because it's so small. It's just some nice picture, of course. This is the historical center in the night. Also in winter we have some snow. It's quite nice picture in my opinion. Here another part of the historical center on the top of the mountain. Also on the countryside, just in front of the big mountain. But more or less that's all, okay? It's pretty small. Talking about the University of San Marino, it's quite young. It's been created in 1985. And we have this program. I'm working actually in the civil engineering field. This course is specialized in earthquake engineering for environmental sustainability. We give to the students advanced knowledge in the field of materials and civil structures, as well as environmental aspects. And here's our palace. We have just one floor. We have very few students, but it's nice to have this very good relationship with students. We have small numbers, so we can create something that is really productive for them. And before starting with my talk, I would like also to present an experience that my student Chiara had here. In fact, some years ago, she spent the 4th semester here working with Gloria on the bachelor thesis project. Yeah, and also with Rome. Yeah, it's some nice picture of her, and she enjoyed a lot this period here. The aim of her research was the evaluation of the efficiency of some GFRP bars for the reinforcement of concrete structures. And she designed all the setup, and also she did some material testing. But today the topic is really different, and let's start with the seminar. As you can see here, is something computational, more related to the computational mechanics of Kirchhoff plates using strain gradient theory. So the aim of the talk, the aim of the research is the development of a finite element method for laminated Kirchhoff plate, so thin plates, including the non-local strain gradient effect, which could have some effects at the nanoscale. With respect to the literature, this method is able to study general stacking sequence of orthotropic layers with different orientations, different boundary conditions, including membrane bending coupling. But for the first time, what is the real novelty of the work is the possibility to introduce and to study arbitrarily shaped domains. And we will see later. Just some words about non-local elasticity. Higher order elasticity theories are becoming more popular due to the increase, as you know, of components at the micro and nano scale. In these structures, very particular structures, the behavior changes according to the size-dependent effect. For example, the internal length scale and non-local properties. And among these theories, the one I have considered in this research is the strain gradient elasticity theory. According to this approach, the value of the stress components depends not only on the strains in a specific point, but also on the Laplacian, or the divergence of the gradient of the strains. Here's some mathematics. I promise not to go too deep in the mathematics, but that's some expressions that are needed. According to this approach, the stresses here on the left, sigma, depends not only on the classical stresses, but also on the divergence of the strains. As you can see here in the first line, you have the Laplacian, and you apply this Laplacian to the strains, and at the end, you have the classic stresses, the very well-known stresses, plus an additional term, which is controlled by the parameter L, which is just a number. Yes, I finished the sentence. It's just a number that takes into account the micro-macro interaction within the material. Please.
Can you give some physical insight on, I mean, is there some sort of physics reason for this?
Yeah, this theory are coming from the new materials such as nano or microstructural materials, which have a sort of internal structure. And in this kind of material, you can have this relationship between the points, with the molecules, let's say, and they create a sort of interaction. So maybe if you have some stresses in a point, the particles of the materials interact between them, and so you can create a sort of global effect of this material according to this size effect. And so by controlling the parameter L, you can increase or decrease this effect. Of course, if you put L equal to 0, you come back to the classic elasticity with no interaction between the particles.
So is it fair to say that it's an effect of very local changes in material properties?
What do you mean with the changes of material properties?
Well, I mean with...
because the material, as you will see later, the material is the same, but you are adding this part just to have a sort of interaction within the same material. This is an exemplification, okay, of more complex material that are currently being used in many engineering applications.
But are these discontinuous differences in properties like you have between layers, or are they?
No, within the same layer, within
the same layer.
Yeah, within the same overall behavior. Okay, but you can have more complex material, of course. This is just, let's say, simple approach for the non-local stresses because you have one single parameter. You could have more parameters to increase these non-local effects. So, but what is my research focused on is the development of finite element model. Just a few words also about the finite element model. And when you have this kind of approach in which you have the derivatives of the strains and so derivatives of displacement at the end, you need a particular finite element formulation which requires not only the continuity of displacement, but also the continuity of the derivatives. And so we have C1 continuity requirement. And typically, this is something you can find in every book of finite element. If you are using C1 continuity requirement, you can develop conforming or non-conforming approaches. In the conforming one, you have a the continuity requirement is fully satisfied. Instead, in the non-conforming one, you can reduce the order of the continuity requirement, but in any case, the convergence of the numerical approach is guaranteed. So this is a sort of literature review about some C1 finite elements. I will talk only about 4-noded rectangular elements in the following. And as far as the conforming approaches are concerned, you have the Bogner-Fox-Smith element with 16 degrees of freedom per element, which means 4 degrees of freedom per node, and the corresponding counterpart, which is the Adini-Cloche-Meloche element with 12 degrees of freedom. Typically, you develop the one on the left, and then reducing the order of continuity, you have the non-conforming approach. This is classical C1 finite elements, so more or less the same thing I've already told you. You have the conforming element with 4 degrees of freedom per node, and you have not only the displacement, in this case it's W, the vertical displacement of the plates, but also the derivatives, until the mixed derivatives up to the second order. The non-conforming one, instead, has this only 3 degrees of freedom. So the mixed derivatives is missing. Difference, the types of degrees of freedom are different. Similarity, we need to use the Hermite interpolating polynomials for the approximation of the degrees of freedom. In any case, the element I'm using is as four-noded rectangles. And here you have the difference of the degrees of freedom, 16 versus 12 degrees of freedom. This is for something which is valid for the classic thin plate. So in Kirchhoff plate, if I don't have the non-local elasticity, I need this approach to model the bending behavior of the plate. And the membrane behavior, instead, is approximated by using the classic Lagrange element as the one you can find in any commercial codes. Yeah.
What's the difference between the plate and the membrane?
The one I shown you is the bending, so W, the vertical displacement. The membrane behavior is the in-plane behavior. So let's say if this is the three-dimensional space, then W, which is the vertical displacement or transversal displacement, if I have vertical loads, for example, but I can have also membrane behavior if the plate is loaded in the plane. So I can have U and V as horizontal displacement in the plane. And in that case, we need the classical Lagrange interpolation for those displacements. Let's go deeper inside the non-local theory, so gradient elasticity for non-local, for Kirchhoff model for plates, for thin plates. The kinematics is the same, as you can see here, maybe in a more compact notation. What is different, as you can imagine, is the constitutive law, because it's the one I've already shown you before. It is just the same in compact notation. You can see that you have the parameter L, which is related to the divergence of the strains. And again, if you put L equal to 0, you can find the same Kirchhoff model. Once you have the stresses, here, just to be more complete, K is the layer. So I'm just introducing a plate, which is maybe I go back to the previous plate. As you can see here, the plate is made by several layers. We can have different properties, different orientation, orthotropic, isotropic, whenever you want, because at the end the theory is an equivalent single layer theory. So we create a sort of homogenization of all the layers. We put all the properties as an integral on the plate middle surface, which is the main domain of our model. As here you can see some definition of the stress resultants, the membrane forces, and the bending moment or twisting moment. As you can see here, if you perform the integration, you can have an influence of the non-local properties even in the forces. Yeah.
Is that a different Kirchhoff than the electrical person?
I have
Kirchhoff's law.
yeah, many Kirchhoff. I think this should be the same, or maybe I'm not sure about that. I have to check. Nice question, because we see many times Kirchhoff, but I will see. I will check later. I'm not sure about this. So that's some here. Once you have this definition of the stresses, we can continue and develop all the model. As you can see here, we have some complex operator here. Complex means difficult, not some complex number, but as you can see here, we have higher order derivatives up to the second order. Since we have introduced the strain gradient hypothesis, we have higher order derivatives of the displacement in the model. And this is a problem for the development of the finite element. We don't like the derivatives of displacement in the model, to be honest, because we need to use Hermite elements, as you will see later. Here's the strong form of the equation. Maybe it's a more compact notation than the usual, but I just want to show you something later. This is not important for the presentation of today. You have the same form as the classic one, but the meaning of each term is different, because in the stress resultants you have the non-local component, as I showed you before. That's some definition, just to say that you can include the static behavior, dynamic behavior, free vibration, of course, and also buckling. And so just a sum up of this theoretical part, the bending equation is a sixth order partial differential equation, two more than the one which characterized the classic theory. If we need also to consider the membrane behavior, we have to add two more equations, which are both fourth order partial differential equation. Overall, we have 14, and the order of the problem is 14, and so we need 14 boundary conditions to solve the differential system. And here you can see all the set of the boundary conditions, in which you can see that we have also some stresses, some stress resultants which are related to the non-local effects. Maybe from the physical point of view, this is something that needs to be more investigated, because it's sometimes not so clear which is the effect of non-local forces in the boundary condition, but this is not the aim of the work. So once you have your strong form of the governing equation, you need Hermite interpolating function because of the presence of the derivatives. And now we can develop the conforming and non-conforming approach for the approximation of our primary variables. The problem is that with respect to the Kirchhoff model, with the classic Kirchhoff model, with the strain gradient, we have increased the order of the derivatives. And so, as far as the bending degrees of freedom are concerned, we need C true continuity requirement. And so we need to modify something with respect to the approaches I've shown you before. So from one side, we have bending degrees of freedom, C2 continuity, which means continuity up to the second order of derivatives. But since we have introduced the derivatives of displacement due to the strain gradient, this effect is also included in the membrane displacement. And so now we have also to enforce C1 continuity even for the membrane degrees of freedom, which is different from the classic Kirchhoff theory, because in the classic Kirchhoff theory, the membrane behavior is C0, which means only continuity of displacement. And this was the reason because we can use the Lagrange finite element. So now we have this situation. The membrane state has to be approximated by using C1 formulation. And so in this case, we can use the same approaches that normally is used for the bending behavior of classic thin plates. And so for the membrane state, we have the Bogner-Fock-Smith element if we want the conforming approach, or the ACM if we want the non-conforming approach. Here is just a different notation, but we have the displacement itself and derivatives of first order plus the second order mixed derivatives. And for the non-conforming one, we don't have the mixed derivative here, but it's the same we normally use for the bending behavior in Kirchhoff. but now has been used for the membrane approaches, for the membrane behavior, for the membrane displacement. And now let's go to the bending approximation. So we need something which enforces also the second order continuity, and we have this extension of the previous approaches. So we have the conforming one, which has 9 displacement parameters per node, as you can see here. We have displacement, first order derivatives, second order derivatives, mixed derivatives of second order, third order derivatives, the mixed one, and also the fourth order derivatives of displacement. And the counterpart is the non-conforming one with only 6 displacement parameters per node. So just to make a sort of recap, overall we have, if we consider a conforming approach, we have 4 displacement parameters for the horizontal, for the in-plane behavior in one direction, 4 displacement parameters in the, for example, y direction, plus 9 displacement parameters per node in the vertical direction, if we're using the conforming approach. Then you can make the calculation on how many degrees of freedom I need overall. The non-conforming one instead has 3 displacement parameter per node in x direction, 3 in y direction, and 6 in the z direction. So it's a lot of parameters per node, especially in the conforming one. Here is just the strategy you can use for the definition of the interpolating polynomials of higher order. Is that something quite typical procedure that is related to the typical procedure, and in the box you can see the terms that are omitted in the non-conforming approximation. But more than this, which is maybe difficult to interpret, we can have the graphical representation of the Hermite interpolating function for the bending behavior. This is the case of the conforming one. As you can see here, you have something. Imagine to cut this picture, you can have the same Hermite function, which are mainly used also for beams. If you have the Euler-Bernoulli beam, you have the same interpolating function, which should be a Hermite function as well, in which you not only you control the displacement, but also the first order derivatives, which is the rotation. And these are the nine function, Hermite function for example, one node conforming element, and the 6 function for the non-conforming one. So since we are talking about finite element, we need to develop the variational formulation and then the weak form, and at the end we can obtain the discrete form of the governing equation. As you can see here, this equation is related to the generic element E. In this element you have the stiffness matrix, geometric stiffness matrix, clearly the nodal degrees of freedom, mass matrix, and the load vector. I'll show you all the form of this matrix because otherwise you get bored. But as you can see here, the part that I want to underline is the fact that in the stiffness matrix, you have the classic part, which is the typical matrix you can find in any finite element about Kirchhoff plates, plus another matrix which is related to the influence of the strain gradient. And this matrix can be decomposed, as you can see here, in 4 further matrices. And here you have the definition of the matrix themselves, which is the form is B multiplied by the constitutive matrix multiplied by B, which is typical because B is the matrix which includes the derivatives of the shape function or interpolating function. Just to show you the influence of the eigenorder derivatives here, the matrix which are related, the second and third row, these matrices are related to the strain gradient effect. You have eigenorder derivatives, and this, once again, the reason we need this kind of formulation. These are the other matrices, geometric stiffness matrix, load vector, and mass matrix. But I don't want to show you all the details. So, please tell me if I'm late or if I have to speed up. Okay. The problem is that if I have a regular domain, like square matrix subdivided into regular element, I don't have any problem also in terms of mapping. And first of all, I will show you some application related to regular domains. Then I will increase the level of difficulty to deal with arbitrary shaped domains. So this is the approximation of the first order derivatives, second order derivatives, and third order derivatives which are needed in the formulation. They are quite simple. Please keep in mind this expression because later it will be very more complex. And let's start with some convergence analysis. In this case, you have the convergence in terms of backing load for a cross-ply laminate or angle-ply laminate. As you can see here, if the dot line is the relative error of 1%, we are really below that line, okay? So the formulation is accurate and is also convergent. Something that I want to underline is the difference between conforming, the orange one, and the non-conforming line. So the non-conforming, even if the continuity is not fully satisfied, is faster and even more accurate. Maybe because the fact that I need more degrees of freedom in the conforming approach, it creates a sort of additional restraints which could entail some it could entail more time to reach the convergence. Okay. Yeah.
When you say 16 by 16 mesh,
yeah,
what are we talking about?
We have to, sorry, nice question. I'm talking about a square plate.
One plate.
It's a plate, yeah, in which I'm using 16 elements in x direction and 16 elements in the y direction.
Okay, but there are many plates.
Yes. The domain is one square plate, and it has been subdivided 16 by 16. So the overall number of elements is 16 times 16.
No, I understand that, but you have a humongous amount of plates. It's not just one plate.
Yeah, just one plate. Yeah.
No. The test you're doing is one plate.
Yeah.
But if you're gonna do a building, you've got a lot of plates.
Yes.
Because my question at the end will be how much does it cost?
Okay. No, yeah. But the problem is that now it's just a matter of implementation. So I'm taking on as a reference only one. And you can combine, create the domain you want with some limitation. Of course, I will show you later. Critical backing load yields some numerical results just to prove that the results are really similar to the one you can obtain with the Navier method. Navier is a semi-analytical model, but it's valid only for some cases, such as the cross-ply plates. And I don't want to show you all this number, but the important thing is that the results are accurate independently from the geometric ratio of the plate. So maybe you can have also a rectangular plate, not only square plate, and also for different level of orthography of the plates. Here are some other results. As you can see here, there is a very nice match between the analytical solution and the numerical ones. Here, once again, for the backing load, aniaxial, biaxial, different lamination scheme, and even in this case, as you can see here, the lines are the ones obtained analytically, not only for classical theory, but also for the non-local one. And in any case, the solutions are quite accurate. If you see a discrepancy here, is related to the use of the conforming plate, because here maybe A over B is the ratio of the size of the plate. 5 means that you have a rectangular plate. In that case, the elements, since we are keeping 16 by 16 mesh, the elements are more stretched, elongated. So my interpretation is that the conforming approach is suffering from the distortion of the mesh in that case. Here some other results just to prove that the accuracy of the finite element model is reliable for different kind of restraints. Here the solution is analytical and is not implemented by me, but has been taken from the literature. Some other result here in this case is a different lamination scheme that you cannot solve by using the analytical method. This is the main reason I introduced finite element. finite element is needed to solve something that I cannot solve, for example, with the Navier method, which is only for cross plane or angle plane with simply supported boundary condition, but it's a sort of generalization. Here also some of the critical shapes mode here for the same lamination schemes. Let's go back to the free vibration, but it's just a sort of repetition because you can have the same result that I have obtained for the bugging analysis, the same accuracy for both classic theory and in this case, sorry, for the non-local theory. In this case, once again, a 16 by 16 mesh has an accurate result. Some other consideration here, but the final remark is always the same, that the results obtained numerically by the finite element are accurate. Here I can go faster. Something more interesting maybe for you is the free vibration in thermal environment. You can adapt this model also to introduce a sort of thermal load or hydrothermal load, and even in this case you can have a very good match between the Navier solution, analytical solution, and this approach, as you can see from the overlapping between the lines and the points and the marks. Some other results related to the different boundary condition. As you can see here, we have simply supported, clamped, a mixture of simply supported and clamped edges. Also, you can introduce free edges and mix all together. It doesn't matter because we have finite element and we need only to enforce the boundary condition in terms of displacements and derivatives of displacement. Static analysis here, again, the same consideration. You can see that the non-conforming approach is always better than the conforming one and is even faster in terms of accuracy. Maybe I can reply to your question in advance. Talking about the computational time in this situation, just to make also a comparison between the non-conforming and the conforming one. For this kind of analysis, maybe with my computer, by using a 32 by 32 mesh, I need a couple, maybe 16 seconds for the non-conforming one and a couple of minutes for the conforming one. So there is a big difference between the two approaches because, of course, you have more degrees of freedoms. Here some other results, but more or less are the same consideration about the convergence analysis even for rectangular plates. In this case, we have again the comparison with the analytical solution, and even in this case, you can see that there is a good, good matching between the analytical solution and the numerical solution. Not only displacement, but also the stress components of the plate middle plane here for different loads. Something more interesting also is the representation of the stresses through the thickness of the plate. As you can see here, this behavior is something related to the fact that I have lamination schemes made by orthotropic plates with different orientation. And even in this case, there is a very good accuracy between the numerical solution and the analytical one for different levels of for different value of L. You can see here, increasing the value of L, you can have different profile of stresses through the thickness of the plate. So some consideration at the end of this first part. We can notice a strong effect of the parameter L, what I mean is we can, by modifying the value of L, we can obtain different structural behavior, as you can see here. But what is more important for me, since I'm more focused on the implementation, is that the proposed model and proposed implementation is valid and accurate. And here is just an extension to the generic lamination scheme with different boundary conditions. As you can see here, you have different stiffnesses because of this, as you can see here from the slopes, for different value of L. So this is something more, what I have explained until this moment is the use of this procedure for rectangular plates or square plates. But typically you don't have this kind of regular element. You can have distorted plates with maybe with also circular domains, something like this. And so my point is that how can I extend this formulation to study arbitrary domain like this one? We need to modify the mapping of the derivatives up to the third order, which requires now more complex expression with respect to the one I showed you before. Please keep in mind the slide in which I have written the expression of the derivatives. So now we have to describe this kind of element. Starting from what? Starting from this master element. So what I have is my master element for rectangular 4-node element with the degrees of freedom I have introduced before. And I need this element to be mapped in this element here on the left. So we need to create a relation to move from the physical element to the natural coordinates element, to the master element. So one is xy, geometry, the definition of the geometry in the plane. And on the other side, we have the master element in natural coordinates, which is regular. So the idea is to develop an isoparametric mapping, like the one you can find in any commercial code, but for Lagrange element. Formally, you have the same expression here. If you forgot about the Hermite polynomial, you can have this similar expression for Lagrange element. The problem is that Hermite polynomials interpolate not only the displacement but also the derivatives. And so if we use an isoparametric mapping, even in this case, we are interpolating not only the coordinates of the nodes, but also the derivatives, the geometric derivatives in that point. And so this is more complex. Here, phi is the Hermite polynomial, and so we need to multiply and make the summation here and multiply each term of the Hermite polynomial with the corresponding geometric parameter, which could be the coordinates or the derivatives of the boundary, let's say, or the geometric shape of that element in the node. So, how can I compute these parameters? We can use the methodology proposed many years ago in the 1988 by these authors here, in which we can obtain the geometric parameters using any classic 8-node Lagrange isoparametric element. What does it mean? We can take any commercial code. You can choose, there is no limitation. We describe the geometry also with curvilinear edges, and at least we need 8-node element if we want to describe a curvilinear edge, because 4-node element with a Lagrange element cannot describe any curves, only lines. In this case, if I describe the geometry in any commercial code by using classic 8-node Lagrange element, I can obtain this description, x and y, because it's interpolated by using the well-known Lagrange function. And so if I have x and y, I can derive this expression by using here Lagrange polynomials. And so I can obtain those parameters that I need here. And this is the strategy. So since the expression of these nodal parameters, geometric nodal parameters, can be computed by extracting the data from any commercial code and then putting again in this model, I can describe this kind of shapes. This is my commercial code. As you can see here is a sort of part of a circular plate in which any element, I don't know if you can see here, maybe I can, no, I cannot magnify, but as you can see here, this element is a Lagrange element in the commercial code with 8 nodes. And by using that element, I can describe curvilinear edges. If I perform the procedure I just explained to you, I can define the same plate in my model. What is the difference? The difference is that, for example, talking about this element on the top, you have only 4 nodes. 4 nodes normally with the Lagrange element can create only straight boundaries. In this case, by using Hermite elements, you can describe curvilinear edges because you have also the interpolation of the geometric derivatives in that corners, in that nodes. And this is the procedure I'm describing the geometry in any commercial code. I'm extracting the data because I know here everything because I have the Lagrange parameters. I'm performing the derivatives to obtain the parameters I need, and then I can describe the same geometry by using Hermite elements. Do you remember the slide I've shown you before about the mapping of derivatives? If I had a regular element, now it's really more complex. Look at, for example, at the third order derivatives here. It's quite complex. You need a lot of parameters because you have in your model, in your weak form, you have the derivatives with respect to x up to the third order, for example, and you need all these parameters. But this is not the main issue. The main issue, I don't want to go in detail into this expression. I will not ask you question about this, of course. But please note how many geometric parameters I need. And these parameters are all related to the coordinate sense between the two models. It's not so easy. Here you have this 4 plus this 4, and also you have a lot of more definition that I have omitted here, as well as here the derivatives of the Jacobian matrix. It's a lot of terms just to perform this mapping. Here's more or less what I just told you. So let's see some numerical application. Yeah.
Can you clarify, because when you do the Lagrangian with 8 nodes,
Yeah.
you have 24 degrees of freedom.
You have, sorry?
24 degrees.
Yeah, yes.
Your element on conforming has 36.
Yeah.
How do you do a mapping? Is it right there?
But yeah, I'm not in this case when I'm using the Lagrange element, it's just a matter of geometry. I'm not talking about displacement in that case. I need this procedure just to relate the two geometries, not the degrees of freedom.
Isoparametric implies
Yeah,
that
yeah,
it will be the
isoparametric.
same for both.
Yes, but the isoparametric in the sense that here it is isoparametric, not between 8-node Lagrange element and Hermite element. It's isoparametric because here in this expression I'm using the same Hermite polynomials to describe the geometry that I need for the approximation of the degrees of freedom. This is the meaning of isoparametric element. The use of the same shape function for both displacements and the geometry. But what I'm missing here is in the interpolation of the geometry is the derivatives of the nodal quantities in the corner that I have, and this is why I'm talking about the Lagrange element in the commercial code, because I can extract geometry since the interpolation of the geometry is known. I have the Lagrange interpolating function, and once I have the complete description here on the left, I can extract the coordinates, perform the derivatives, put in here, and perform the isoparametric model since I'm using the same shape function for both displacement and geometry. I hope that is more clear. Maybe
We'll take it on paper.
yes. But maybe later we can discuss. We can investigate more. So let's talk about this application. This is a square plate. You have mesh 1, which is the classical regular structure. Mesh 2 is just a mesh rotated. In this case, is structured, which means the derivatives of the geometry are smooth, but distorted, because if I'm keeping the same reference system, which is the classical one, horizontal and vertical, this is a sort of distortion. Mesh 3 is unstructured and distorted. As you can see here, you have a big distortion and is not anymore structured. This is completely arbitrary. In this case, we perform. Why I'm choosing this particular geometry? Because for square mesh, I have the analytical solution. I need that to perform the comparison just to check the accuracy. So here is the convergence of the first frequency in terms of relative error, in this case. Here on the left for a single isotropic layer, on the right, a laminated plate made of, I don't remember how many, made of several isotropic plies. For the non-local, here on the right, you have you have this value of the non-local terms. So we are in both situations, we have non-local theory, non-local elasticity. As you can see here, you have some convergence results that are very good, and these are related to the mesh 1, of course, but also mesh 2. So we don't have any kind of problem even for the second one. Second one is the distorted but structured. As you can see here, I have put an S or an NS. Why? This is something I need to explain better. Once you have this kind of distorted mesh, here you can perform a sort of smoothness procedure, because if you compute the derivatives of the geometry here in this element 4 in the node 3, for example, the result is different in the element 3, same node. Why? Because I'm using a Lagrange element to perform the derivatives of the geometry. And so we could have a sort of discontinuity in that node in terms of geometry. And so if I'm performing a sort of smoothness procedure, I'm taking the value here of these derivatives here, 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 and here. I'm making the mean value. Maybe you can find also some more sophisticated, but doesn't matter to my aims. And so you can have a sort of smooth result. But let's see what happened. Of course, in the mesh 2, there is no difference between the smooth or not smooth result. Why? Because the results are the same in the 4 nodes and the mean values is the same. And this is the reason why, if you check mesh 2 smooth and not smooth, you have the same complete overlapping. But let's check mesh 3. The purple lines here and here is not convergent. It's not convergent when you have the smoothness procedure. Instead, if you are not using the smoothness procedure, the results related to the mesh 3 are better but not so good. Later, let's give some consideration now. So, by the way, you can have more or less the same behavior between the conforming and non-conforming approximation that I've shown you for regular meshes, okay? So in general, the convergence is the same for the two mechanical configuration. So single isotropic layer or multi-layer plate. The smoothness procedure has no effect when the initial mesh is structured. So mesh 1, mesh 2, no problem. I'm more focused this time on mesh 2 because it's distorted but structured. Different situation when the mesh is unstructured, such as the mesh 3. When the smoothness procedure is applied, the solution is not good. But on the other hand, if the smoothness procedure is not implemented, okay, I have a sort of geometric error, but the solution is, let's say, almost good. It's 2 or 3% of error, but at least it does not diverge. In general, for the structured mesh, the convergence is monotonic for both the formulation, and there is a constant slope for non-conforming and conforming formulation. In general, once again, the non-conforming formulation is faster in terms of convergence than the conforming one, and the accuracy is good in any case. So, just to make a sort of conclusion now, maybe this approach, no, without maybe, this approach is not suitable for this case. So, I need for sure something which is related to structured mesh, even if they are distorted. I will show you some example of distorted but structured mesh. So maybe we need
Sorry, Michele, if you can kind of wrap it up, we have 10 minutes left.
Yeah, I just need 2 minutes to finish.
Yeah.
Okay. So let's see very quickly some results here. We have quadrilateral distorted mesh. They are structured, yes. So I should have no problem. As you can see here, we have a very good convergence. This is for classic elasticity. When you see L equal to 0 is classic elasticity. And if you have 0.1, it's the case of non-local elasticity. Something that I have to specify. In this case, you can see a reference solution which is obtained by classic finite element, since classic elasticity can be solved also by commercial codes. Instead, we don't have the reference solution for the non-local theory because it's not implemented in any commercial code. What I have done here is the comparison between non-conforming and conforming mesh. As you can see here, in addition, you don't have any difference between the smoothness or not smooth result because the mesh is structured. Here is a different, this is mesh A, mesh B, the one I showed you before. But what is more important is that with this approach, I can study very distorted elements like these ones. I don't want to go inside the result because more or less you can extract the same observation. You can perform the mechanical behavior. You can study the mechanical behavior of different plates with different boundary conditions, different lamination schemes. But in this part, I'm more focused on the geometry, distorted geometry. As you can see here, you just need an Hermite element with 4 nodes to describe this kind of curved domains, and the results are still good. Here we have some more geometries. As you can see here, what is important to notice, look at the position of the node 3. This is a quadrilateral element. Why is a quadrilateral element? Because my master element is a 4-noded rectangular element, and it is very distorted. As you can see here, this edge is really distorted. As you can see here, 1, 2, 3, 4 nodes, even in this case, here, very good, very important, significant distortion here. And the results are still accurate. You can continue, you can have many other applications, always related to distorted element, which was the aim of this research. So you can here, of course, you can have no limits on the description of the geometry unless it is structured. This is the main limitation of the work. So in general, just conclusion here, the numerical approach is accurate and reliable, the convergence is good. In general, the non-conforming approach is better than the conforming one. And the conforming one is, in addition, is also more sensitive to the element distortion. You don't have any limitation on the boundary condition, no limitation on the lamination schemes, as typically you don't have in finite element. So let's check if the initial aim has been reached. The aim was to study plates with general stacking sequence with orthotropic layers, different boundary conditions, including also distorted domains. And so I can say that the goal has been achieved. Some future works. So now, just to make a sort of diagram, we are here. We have completed the isoparametric mapping for distorted element is done. We have studied the linear mechanical response of plates with arbitrary domain, done. The next step is the linear fracture mechanics of thin plates in gradient elasticity. Talking about gradient elasticity, in which you have a sort of link between all the particles, it could be very nice also for the fracture mechanics, in which you have a sort of damage in a plate, and you can see how the behavior turns out after this collaboration within the particles within the material. Final step here, extension to the nonlinear elasticity. So before concluding here, you have some main references if you are interested in investigate more some aspect. So I hope that I've been on time. I hope also that you enjoyed the presentation. Before leaving this the stage for your question. I would like to thank Gloria once again for the invitation. It's been really nice for being here. I really appreciate also your presence here. Thank you.
I have two questions. So the first is, you said you have an analytical solution to this one element. So if that's true, and is the analytical solution closed form is exact, in other words, that you're comparing your results to that?
Yeah.
So the obvious question then is, why not just use the analytical solution? You already have it.
I have, but only for some cases. Cross ply, so 0, 90, 0, 90, or angle ply, minus 45, 45, and only for for simply supported. If you need to study a plate which is clamped, or one edge clamped, one edge free, you cannot study with analytical solution. And of course, you can have only for square or rectangular plate. The Navier solution, for example, is valid only for square plate.
That makes sense. Okay, and then the other question I had was, you mentioned, and I sort of missed the very beginning, so then I was like the whole time wondering, well, what the heck? So you said strain gradient.
Yeah.
And that's why you went all the way through all of this. You added some extra term. But in classical beam theory, plate theory, shell theory, and all the finite elements that are associated with that, we all have strain gradients. What is different in your strain gradient from what's already done?
You mean I go back to this?
I mean, a beam and bending, the strains are linear through, the depth of the beam.
But
And it's the same thing with a plate, but it's in both directions, for example.
But with strain gradient, okay, this one. This one is maybe it's better to go. This one. This one is not classic theory, because if you look here, if you don't have this part.
Right, and I'm asking, why are you adding that part? What is it specifically? That's what I didn't get.
Yeah,
I don't understand.
this is nowadays there are many theories, non-local theories. You can have stress gradient, strain gradient. You can have micropolar theory. There are many theories just to take into account this sort of collaboration within the particle, within the materials. So when you have sort of nanostructured materials, which are very, very common now, you need to modify this constitutive law. I'm not focused this time on why I chosen this one. I could have chosen one theory, micropolar, or this one. I've tried this one because I have seen in the literature many works about this theory, but I notice also sort of confusion when you are talking about the implementation of the finite element, because something is missing, maybe, no? Because here all the main difficulties is related to the use of Hermite function. Since for me, when I started this research, it was interesting to see the effect of Hermite interpolation. And my question was, why nobody is using Hermite interpolation? Now I understood the problem, that you have a really complex mapping when you have distorted element. And so I started to discuss this particular problem with this kind of theory, because I wanted to underline the effect of the interpolation, and especially when you need to implement for example, in a MATLAB code.
Okay, I'll have to look into it more. Thank you.
Okay, many questions here. Yeah.
I'm still having a little trouble understanding the problem. So if you have isotropic plies, so the only difference between your 45 minus 45 and 090 is just the orientation of the boundary plane of your plate, right?
No, when I have 45, for example, you have, let's imagine this is a square plate, okay? Isotropic, no problem. You have the same property in each direction. When I have orthotropic plies, the plate is the same, but let's, for example, orthotropic plate could be a fiber reinforced plate.
Yeah, obviously that
Yeah.
makes a difference, but you were showing pictures of these tilted elements.
Yeah, but
Well, those isotropic plies.
in that case, it was isotropic because I needed, let's go back to this figure. This is this one, correct?
Yeah.
It's just a generic mesh, distorted mesh. And as you can notice here, I haven't used orthotropic ply. I used isotropic because I needed, it was difficult to implement the orientation in this case mesh 2 by keeping the same reference system. So in this
So it's
case,
purely coordinate related.
yes, in this case it's
Just if they're orthogonal.
yeah, but
Okay,
since I needed to perform the comparison with the analytical, and here the comparison is done since you can see the relative error. So I'm making the percentage error with respect to the analytical solution. In that case, I needed the isotropic one layer or multiple layer isotropic, which is a composite in any case.
Wouldn't it be different? Oh, you mean each one is isotropic.
Isotropic,
They have
yeah.
different. Like,
Yeah, so in that case, I don't have the orientation.
Greens.
Yeah, let's say steel, aluminum,
Yeah.
something like this. Just to see that it is still is always a composite, but here the focus is on the mesh 2, which is distorted. And I needed this kind of mesh just to make the comparison with the analytical solution. Yeah.
Your plate is essentially two triangles.
Yeah.
And distorted and unstructured mesh is, I mean, you can probably triangularize a Klingon.
I was
I don't
expecting
want to
that
make
question.
them into,
Yeah.
you know, laminated,
Yeah.
because that would be really scary. But if you do triangles and then do those types of mappings, do you think you would get more unusual?
Oh, okay. If I understood well, you can you are saying that if I'm using, for example, two triangles to meshing for the mesh of a rectangular plate is easier. Indeed, the triangle is more versatile, is more can adapt better to distorted meshes. The problem is that okay, if you have classic Lagrange element, you are right. But the problem is that when you are using Hermite parameters, Hermite interpolating function, like in this case, and since we have higher order derivatives of the displacement, we need the Hermite interpolating function, as at least in this case, in this particular formulation. With the triangle, it's quite difficult to have, for example, the mixed derivatives in a point of the triangle and then interpolate them. That's the problem. There are many solutions for C1 continuity with C1 continuity requirement with triangles. For example, the Argyris triangle or Bell triangle. Okay, for C1 they could be okay, but the problem is that when you are coming to the strain gradient theory, you have also to enforce C2 continuity requirement, and then the let's say the implementation, the development of this particular element, C2 element, starting from the C1 that are already known, could be difficult. I tried, I have some references. I will work on that because I think that I will avoid many difficulties related to the mapping, such as structured or unstructured mesh by using triangle.
But you will lose accuracy.
I will see. I never tried triangles, but maybe.
That's why a lot of people who do finite elements start with triangle and then they move to a quadrilateral.
But it will be interesting also in terms of implementation. Yeah. Triangle will be nice. I have some colleagues also that are working on triangular interpolating. Our goal is also to define this kind of problem by using triangle. We need more time, maybe. Thank you for the question, by the way.
Yeah, if you do create a laminated Klingon, you can come back here, give a lecture, and I'll give you a $1 bill.
Okay, it's a promise. Okay, thank you very much.
The notes, we thank our speaker.
Thank you so much.
I hope you enjoyed. I haven't the time to give all the details, but maybe if you are interested, we can.
Well, right now we're gonna go to look at how these laminates bend into a cup.
Yeah, even a better solution. Thank you very much once again. Thank you.